Hello, good afternoon, everybody. So, as this part of the slide says, my name is Steve, and as this part says, I'm a little bit of a geek. If we've all turned up to the correct room, this is a talk about Ada Lovelace and the very first computer program. Over the next 39 minutes and 37 seconds, we're going to be looking at that very first program, how it works. We'll transform that original program into JavaScript. Why JavaScript? Well, it is the one true language. Thank you. And ask that important question, was Ada really the first programmer? But before all of that, who am I? What have I done to deserve a place on this stage? Or as this slide should be called, the ego slide. This is where the speaker will brag about themselves for 10 minutes while everyone else goes and doom scrolls Reddit. Well, not at the moment, they won't. US East 1 is out, but, we'll get by. So who am I? What have I done? Well, I'm a general-purpose, unemployable computer geek. In my time, I have built pretty much everything for every system. I did a whole load of games. I've done a whole load of cloud education technology. I've currently now written 8 books, mostly about computers. I mess around with all techs. I build a lot of emulators. I like old computers. And I've done these VR things. I do like my open source, so I advocate that a fair bit. Lots of really interesting, lots of important, clever stuff. But what's important is not what's on that slide. The bit that's important is what isn't on that slide. I am not a computer historian. I don't work at Cambridge University studying the history of this stuff, looking at Ada's original letters. I am not an influencer-type person. I don't go around creating narratives for the DevRels lot. I am just someone who thought, I wonder what the first program was. And then I started looking into it and digging and working stuff out, which is a very long-winded way of saying, if I can do this, anyone can. So, I like Lego. I really like Lego. That's me for scale on the left, by the way. So, what was that very first computer program? It's this. I said I'll show you the very first computer program. Now I have. Can I go to the pub? OK. So this is that first program. It came from a book, a translation from Luigi Menabrea back in 1840. Luigi Federico Menabrea ended up to become the very first prime minister of Italy. That was interesting to me. So this is that first program. So where does Ada come in? Well, Ada, or to give her full name, Augusta Ada Byron King, Countess of Lovelace, was an aristocratic lady from Victorian England, 1800s. And as was the norm in Victorian society, women were not educated. But she was rich. More precisely, her mother was rich because of that name, Lord Byron. Yes, that one, the poet. And because we have a code of conduct, I'm not allowed to use the word for Lord Byron that I would like to use. So let's just say Byron was a little bit of a scoundrel. Is that OK? Is that acceptable? Good. So consequently, they pretty much never met. And Isabella Milbank, the mother, was actually quite happy about that. She ensured, because she was rich, that Ada got a good education and was mostly schooled in maths and sciences. For better or worse, her mother thought that, well, Lord Byron is a poet, and he goes off doing things with, he loves families, just not his own, and he loves wives, just not his own. Let's put it that way. And Ada's mother thought, if Ada ends up becoming like her father and becomes a poet, I really don't want that for her. So she got a series of very good teachers, Mary Somerville, for example, George Boole taught her for a while, De Morgan's theorem taught her for a while. She was well educated. And that's all her mother's doing, because by being educated in science, you're not going to become this run-around poet-type person. The fact that her mother's initials are AI is purely coincidental, but might be amusing to some. And yes, she did die very young. So that's one part of the story, the first programmer. But what about the first computer to run this program? Well, that comes courtesy of Mr. Charles Babbage. He is what would be politely known as a clever bugger. And he was also what you would call a bit of a character. The nice way of saying eccentric in English. He was smart. He would break codes for fun, but then not release them because he thought, if someone knows I can break their code, they'll change their code. A motif that comes up with Turing in sort of The Imitation Game, if anyone's seen that film. So Babbage studied at Cambridge, did a lot of maths, a lot of science, a lot of other things, basically anything that interested him. And one of the things that interested him was the idea of machines that could do calculations. It is said that in a conversation he had with Herschel, the son of the astronomer, he said he was looking through a logbook. And these logbooks were tables of natural logarithms. Because before we had calculators, you had to do this stuff by hand. No one wanted to do these calculations by hand every time, so one person would do it once, they would print the book, and then everyone would buy the book. Only he would look at this book of logarithmic tables and go, wrong, wrong, wrong. I wish to God these numbers had been computed by steam. Now, he doesn't mean that literally, that a kettle would be able to compute these numbers. Well, let's face it, with the amount of smart technology, your kettle probably can do that now. But his idea was, let's get a machine to generate this, because every step in the process has a human in it. A human is doing the maths to get the numbers. A human is taking those numbers and putting them into a block to go to the printing press. Another human is then checking them. So if we can get rid of humans entirely, we can get rid of mistakes entirely. So he came up originally with this. This is a difference engine. And true to programming, Charles Babbage's first difference engine was difference engine number 0. The second was difference engine number 1 and difference engine number 2. Now, we're talking 1822 to 1830 at this point, and this would do one calculation. It would do subtraction. Because it's called a difference engine. Only nothing is that straightforward. Of course it doesn't do subtraction. It's not called a difference engine because it does subtraction. It actually does addition. Makes sense, right? Babbage computers. Naming things is hard, even in the 1800s. So he created this difference engine that doesn't do differences, but does additions. It's called it because of Newton's method of divided differences. It's a way of computing calculations. But that's all it does. But it can do a lot of them, and it can do them quite quickly. But if you want it to do a different calculation, you've got to reprogram the hardware. Now, as you can see, the hardware on this is a whole bunch of gears. Rebuilding the hardware is a bit complex. So you don't want to keep changing the hardware. So he had the idea of, well, let's build a different type of engine, an analytical engine, where you don't change the hardware, but you have some kind of softish ware to run on it. And he called it the analytical engine. And this is a genuine computing device. This is one of the plans on the right. There were books and books of these plans. This comes from Plan 28. And this would do general purpose computing. This is 1837. That's a picture of part of it. Where's the other part? Doesn't exist. Never got built. Why? Well, remember I said Babbage was a bit of a character? Well, he kept running out of money for these machines. These are big, expensive machines. They have to be manufactured very, very precisely. So you've got to pay people good money to make them. Babbage is running out of money, and his way of getting money and getting finance was to go, oi, you, cash now, need cash, good machine, give me cash, build machine. Anyone here ever dealt with VCs? Anyone discovered that that technique works well with VCs? No, it didn't in that time either. So this machine never got built. But this is essentially the first computer that we want to run the first program on. So, about that program then. Well, as I say, we're coming back to Menabrea again now. So this is the book in which it was exclaimed to the world, look at this machine, isn't this big and clever? Babbage went to Italy in Turin, which is the northeast side of Italy, and he gave a series of talks about the analytical engine. He thought, if no one in the UK is going to give me money, maybe the Italians will. Spoiler alert, they didn't like him either. But he gave a series of talks. Menabrea wrote it all down, published this book in French, and said, here, maybe someone else will read this and will discover this wonderful engine. Spoiler alert, no one did that either. But he wrote this book in French and published it. I think about 3.5 people bought it in the end. And he thought, well, let's bring it to England. Maybe someone there will read it. Well, not in French, they're not. So Babbage had to get it translated. And who did he get to translate it? Ada Lovelace. Written in hand. That wasn't on the original. She wasn't credited on the original. It was inside the book, but not here, not on the cover. And he knew Ada from a few of his parties. He would hold parties every month in Down Street in London, where he lived. And if you wanted to be invited to his party, you had to be rich, because he liked money, or you had to be intelligent, because he liked having good conversations with people, or you had to be really pretty. Needless to say, I would not have been invited, but Ada was. So Ada was invited along, partly because she was Lord Byron's daughter, and everyone wanted to ask her about Lord Byron. So they knew each other. They'd met a couple of times. A lot of their correspondence was not face-to-face, it was paper. But they had met. He knew that she spoke 5 different languages by the age of 20, so she figured Ada can translate this. They'd already had conversations about this analytical engine he was designing, so she was the right person for the job. So she translated this. But has anyone had a maths teacher here that has said, after seeing their maths homework, show you're working? Has anyone had that? You just get straight to the answer and someone goes, show you're working. Well, Menabray did not show his working. He just said, oh yeah, this is how it all works. And Ada goes, you've missed a bit, mate. So then she had to add it in. And she knew of Babbage's work and how it was going to actually function. And in the process of doing, this book grew in size 3-fold. So it's not just translated, it's translate it, fix the errors, add in all the bits he missed, and then do a series of appendices. This is in one of the appendices in note G of the translation. Just to recap all of this bit. This is note G in the appendices of a translation of a French book that almost no one has ever read. Is it any wonder this stuff got forgotten about for 200 years? But it did. Turing is one of the people who sort of brought it back into light back in probably the 1940s, 1950s. And this is that first program. It's note G. The other notes I could tell you if you wanted, but we are, it's just small bits. It's just ideas. This note is the one that actually puts them all together and says, this is how a program could exist. So what is it? What does it do? It calculates Bernoulli numbers. Yeah, I didn't know what Bernoulli numbers were either. If you study mathematics, you probably know and like Bernoulli numbers, using statistics and things. If you're an engineer, you probably like Bernoulli numbers because they're really great for engineering things. If you're anybody else, they're boring. But they're interesting because this sequence doesn't actually have an obvious pattern. There is a pattern, but you can't look at it and just say, oh, I know what the next number is going to be. So you have to compute it. You'll also notice that it goes from 2 to 4 because all of the other odd Bernoulli numbers are 0. No point in writing about them. But these numbers are useful to people, so calculating this was a good idea. But just because there's no pattern in the fractions doesn't mean there's not a pattern in the decimals, right? Wrong. There's no pattern there either. So, needless to say, Ada thought this is a good example for a machine. Why is it a good example for a machine? Well, let's look at how they get calculated. And it's all fraction stuff. So this is a fairly trivial way of representing Bernoulli numbers. I don't think I need to go through any of this. There's nothing complex about it. There's just, there's ones and there's twos, there's pluses and there's minuses, there's divides and multiplies. There's nothing really there. It's something you can work through. I mean, let's reorg that a little bit. It's still a series of numbers. Still very simple calculations, very repetitive calculations. You can see we take this 2n minus 1 and it comes down here and we add another term, and then we bring this down and add another term. So it's very obviously this is the sort of thing a machine should be doing. And from this little section here, let's actually reorganize that into this setup. Each Bernoulli number requires the previous Bernoulli numbers. We'd said already that other Bernoulli numbers are 0. Each Bernoulli number requires the previous Bernoulli numbers. So there's clearly some process here which lends itself very nicely to programming. How does it do it? That's how it does it. So now we know what the first program was, what it does, and how it does it. Now can I go to the pub? No. Okay, I've got to earn my keep today, I can tell. So let's go down and look at that program bit by bit. Every column does exactly the same thing. The first column is the number of operation, the line number. Anyone old enough to remember basic programming, where every line had a... Some people are admitting to being old enough to program basic. Thank you for your honesty. In basic programming, every program line would have a number, not in the text editor, as part of the actual code. Yep, got it. This is how she decided. Every instruction should have a number. A nice, simple, unique way of referencing it. Nice one. The next is the nature of the operation. What does the function actually do? What does this line do? And there are 4 operations in this program. There is add, there is divide, there is multiply, and there is subtraction. That's it. That's the only operations this thing can do. Fine? It then has, how do we use that operation? What variables are operated upon? V1 times V2, V4 plus V3, and so on. We then have a column for the results. We can write each result into one or more other variables. This is the only line of the program. Line 1 is the only line of the program where a value is written into more than one variable. But it's important to note that this is what was going to happen in the machine. The machine was still big cogs turning. So if you have to turn these cogs to make a number move from one part of the machine to another, that's quite expensive in terms of time of turning the cogs. So you turn them once to move the result into many different places, rather than moving it once, then moving it again. The next column is the indication of the change in the value of variables. It's a bit like a dry run. Not that I'm expecting you to be able to see it, but the superscript is saying this variable has changed this number of times. That's kind of handy, because when you get down, you can see, well, it thinks I've changed this variable 3 times so far. Have I really? And you can go back through the code and check. Any programmers in the room? This column is called the comments. I'll explain it to you later. Here is the comments of what's actually gone on over here. At this point, we're multiplying a value n by 2. So there's the multiply, and one of these variables holds the number 2, and one of these variables holds the value of n. Then we have an n, 2n minus 1, 2n plus 1, and so on. And you probably recognize the 2n plus 1 from the equations that I just showed you. A few things you'll notice here. There's no variable names. There's also no assignment. There's also no ability to multiply by a constant. You can't multiply 2n. You have to load n with the value 2, and then multiply by the variable. But we've got no way of assigning variables. So how do we do it? Well, we initialize the machine in that state. So the variables, when you set up the machine, you basically turn the cogs to say 1, 2, and then n. And those variables do not change. So that variable 1 always contains the value 1. So it can then be used time and time again. And that's it. You can see from the additional comments on the right-hand side how this equation is unfolding. Yeah, that's the same thing again. So, one thing to point out, we'll just run through this quickly. It's very easy. We start off, V2 times V3 goes into V4, 5, and 6. V4 minus V1 goes into V4. V5 plus V1 goes into V... Hang on, wait a minute. We're calculating 2n here. Yeah, V4 is 2n minus 1. V5 is 2n plus 1. V5 divided by V4 is 2n minus 1 divided by 2n plus 1. Anyone spot anything there? Yeah, me too. 2n minus 1 is on the top, in red, or is it blue? So not only is this the first computer program, line 4 has the very first computer bug. We haven't even started and we've got a bug in it. But it is really just a typo. This is correct, this on the left is not. Someone just put V4 and V5 around the wrong way in the printing press. Luckily, when you get rid of that, the program does actually pretty much work. So I wanted to see it working, and I didn't want to build Babbage's analytical engine to make it work, so I wrote it in JavaScript. Very simple set of objects. I'm giving you the operation, the source destination for the variables, and comments. For each line of that program, I put that into a program counter. I look at the operation, I do the actual maths, and I put the result into a variable called mil. I call it mil rather than accumulator because the original analytical engine was calling it mil. Then I've done my calculation, I take that result from the mil, and I put it into each of those variables in exactly the same way that it would have worked, because the calculation was all done here, and then the variables were trickled down via lots of cogs to the store here. Remember I was saying about storing the variable in multiple places at the same time was more efficient? That's the reason. It's got physically a long way to travel to get back to those variables. Increment the program counter and do it all again, over and over again. Remember that? This is the thing we're calculating, which means we need a loop. And here is that very first loop. Here follows a repetition of operations 13 to 23. No explanation of how to do it. Just go and do it again. How many times do we do this? What's that exit condition for the loop? Here follows a repetition of operations that, no idea. It just assumes that you, the reader, know that you need to repeat this a number of times. But every variable in that list is a constant, right? V1 plus V2, V3 divided by V4. So if you do the loop again, you're just going to overwrite the same variables you've just written. No way of doing array indices. No way of saying, well, I've done the first bit of the calculation. I now need to do the calculation in the next set of variables so I don't erase the first ones, so I can add these set of variables to these set. No, it's not in there. The instructions don't provide it. The comments don't provide it. And essentially, no array indices, which means the loop would not have worked. Couldn't have worked. So let's ignore the fact that the first program has a bug in it and doesn't work. Let's try and do it anyway. We have a transformation process where I'm taking, and this URL I think is still up. I have no idea if GitHub is down yet. Every single operation, I take it and I transform it little piece by little piece. And that's what that project is there. I go through each stage individually. Take the operation, it's a multiply. Okay, well, I'm multiplying V4 by V5 and putting it into, I'm multiplying V2 by V3 and assigning it into variables 4, 5, and 6. When I go back and I look at the comments in her code, I know what these variables are meant to contain. So then I can give them nice sensible-ish names like 2n minus 1 and 2n plus 1. Still not sure what is meant to be inside V6, but we'll find out later. Similarly, we do a subtraction. V4 minus V1, yeah, whatever it is. Oh, it goes back into V4. Oh, well, in which case I can use minus equals. Okay, that makes some more sense now. And then by doing this repeatedly, I find out what this 2n minus 1 was actually used for, which is this accumulating total. We do a bit more processing, we do a bit more understanding, and we end up with a loop that looks like normal code. So, after all of this, of finding the bug, does it work? Yes. Obviously, it didn't work first time because I hadn't realized there was a bug in line 4. But other than that, it works. These are those numbers, and the fractions are all approximate. The analytical engine and my computation, obviously, it's not using any sort of fancy number libraries with infinite precision. It's just a decimal approximation, because that's all the original machine was going to be doing anyway. So these are decimal approximations. I just worked back to fractions, and they're pretty close. They're within 1/10,000th of what they should be. So that first program did work. Remember the numbers? They roughly match. You can see here minus 630 there, but 690, they are close enough, I think. So we've done it. We've actually got a working program. Oh boy. This is where it gets spicy. Was she the first programmer? Were you the first programmer, Ada? Yep, Ada says she was, so that's good enough for me. So there were lots of reasons that will be claimed that Ada is not the first programmer. I mean, has anyone here been on the internet? Yeah, horrible place, isn't it? You know, I was almost late coming here. I had to correct someone who was wrong on the internet. But I figured I haven't got the time for that. There are people on the internet who are really mean and will always give some reason why she's not and some reason you should discard it. First off, the code has a bug. Therefore, she's not a real programmer. Any programmers here ever not written a bug? Just the one. Well, two including me, obviously. No, it's just part and parcel of the process. There's nothing wrong in it. I mean, yes, there is something wrong in it. It's a bug. But it's not something you can just eliminate half of history for because you don't like the bug in line 4. And I can almost guarantee that every programmer who says, oh, if you can't be a real programmer if you've got bugs, has probably never even read the paper. So they're not qualified. Another thing that people say, oh, we don't like the notation. These are the same people who will complain about, is it Vi or Emacs? It's Vi, by the way. I'm old enough to remember Vi before it was improved. Or is it spaces or tabs? Those sort of arguments are the same people who says, well, the notation is a bit wrong. We don't like that sort of. No, it doesn't matter. The notation is there to communicate the idea. It's not meant to be so prescriptive. I mean, she came up with a notation that I, 2 centuries later, could read, understand, and then rebuild that program. Communication did its job. It allowed me to understand. So even if you don't like it, it's not problematic. The loop didn't work. Yeah. And we fixed it now. It's not enough reason still. She was translating somebody else's work. Yeah. Is that a massive, massive problem? Bear in mind, she increased the size of that work by 300%. There was a lot of extra working that she put in there. The program was her. That didn't exist in the original. Note G, this program was not in that original. So it isn't just translating. Steve Wolfram, that you probably know from the Wolfram package, Wolfram language, he suggested that Ada Lovelace's main achievement was to distill from Babbage's correspondence a clear exposition of the abstract operation of the machine, something which Babbage never did. Yes, Ada and Babbage would have a correspondence, and Ada would write questions. It's like, this machine, does it do it like this or like that? And Babbage would give an answer. Wolfram, in his comment, is essentially saying, Babbage is communicating these answers to her. All that she did was a clear exposition of the abstract operation of the machine that Babbage didn't do. And this makes her not a programmer. So I'm just going to read that phrase again, but I'm going to replace Lovelace with the word programmer and Babbage with middle management. The programmer's main achievement was to distill from middle management's correspondence a clear exposition, the abstract operation of the problem to be solved, something which middle management never did. Abstracting from a problem that management don't clearly is exactly what programmers do. Oh, I'm just the ideas person, you make it happen. And off goes the programmer to make it happen. So in trying to give a nice little phrase of a clear exposition, Wolfram has essentially disproved his point by highlighting exactly what programmers do. Another thing that often come up is Babbage has already written programs for his own machine. Well, this is another one of these, but did he though? Babbage was interested in hardware. He liked gears and levers. He liked physical things. He didn't really write programs. He hadn't really even prepared them. He said, this machine will work in this way. This is how it will do things. I don't care what you do with them. That was Ada's idea. That's what she wanted to do. Did Babbage even write a Hello World equivalent? Probably not. If we go back and we look at his machine, this is the one from Plant 28 that we saw earlier. This is what he was designing. Can you see anything there that suggests 2 multiplied by 3 goes into variable 4? No, because he didn't come up with that bit. That's Ada. He was just coming up with the techniques. He would have said, oh, this is how this gear moves. And he's never known to have written down any form of explicit instructions for this machine. Certainly nothing that we would consider to be a processor manual. He just says, oh, the programs are going to be lists of states, which in his physical world is, where are the gears at any given time? So clearly, he didn't really write programs in the way that Ada thought of programs, or that we think of programs now. But still, I went on the internet, and I still found people who were saying, Ada's not a programmer. So I figured, right, well, I can't win arguments on the internet. I'll come here instead. So Ada had done a number of other things. There were some comments in the book that she does talk about, and there are other writings that she did as well. And in this, she talks about numbers being representative of words. If we go back to why Babbage wanted the machine, I wish to God these numbers had been computed by steam. He liked numbers, he liked mathematics. He wanted a mathematics machine that did mathematical calculations. That's all he wanted. Ada says, yeah, but if these numbers represented a word, then I could write an algorithm that would generate a series of numbers that would represent words that could write poetry. She never strayed that too far from her father's lineage. She had this idea that words would represent numbers, therefore inventing ChatGPT 200 years too early. She also had these ideas that these numbers could become notes, musical notation. Being a Victorian lady with quite a bit of money, she's also educated in music. And so she had the idea that, well, yeah, numbers could be notes. Well, that's MIDI for you, 1982. And she'd also considered the idea of numbers being some kind of color. Now, I don't know whether she considers color to be RGB or CMYK or HSV even. But she had sort of the idea that maybe one day Photoshop is possible. Although I'm an open source person, so I'll say GIMP, but each to their own. And also, she's really exemplified what it means to be a programmer. The idea of taking something, distilling to its essence, understanding it, then representing a fixed solution. Because that program is fixed. You can't change it while that program's running. No self-modifying code here. She had to quantify all of this back in the 1840s. So I had to have an argument that would win over everyone on the internet, which is, easy, right? So if everyone is saying why she cannot be that very first programmer, if I can find one reason why she should be considered that first programmer, can I win the argument and therefore the internet? Can I find one argument? And this is the one I came up with. Ada has had this idea that these numbers could represent words or music or colors. She's had the idea of creating a fixed algorithm that can run unaided on a machine. Doesn't matter the machine didn't exist. She'd had the idea, she'd create the design. So creating the design for the program, coming up with the program, commenting how programs would work, including a dry run, including comments, she has done all of this. If a man had done all of that, would he have been considered the first programmer? Because, let's face it, if he had come up with just one of those ideas, he would have been called the first programmer. But if he would have been called the first programmer, then she should be called the first programmer. And that's undisputable, dear everybody on the internet. And if she is the first computer programmer, then this is the first computer program. So with that, we have seen the very first computer program, an estimation of Bernoulli numbers. We've seen the algorithm, which is describing, everything down to every single detail. And I think we can prove that Ada was the first programmer. So with that, I'll say I possibly have some time for questions, but otherwise, that's all from me. Thank you. There's a hand for question here.
Which number system did the gears work with?
When someone says that, you know it's a question I want to answer. And the answer is base 10. Even though Boolean numbers were known at the time, they weren't used. If I zip back all the way, you've seen the punchline now, and I show you a picture of the gears, you might just be able to tell here, 9. It was base 10, because that's what humans used. And the idea was, well, if we create it in base 10, then humans will use it and they'll find it easier. The problem, obviously, when you've got a gear in base 10, there's a lot of ways of getting it wrong. It could get stuck partway between two numbers, in which case, then what one is it? When we're working with binary in an electronic sense, the 0 current and the 1 current, quite a way away. Here, there's a lot of room for error. And in the machines, it's not visible. In fact, it's not even on this machine. But there is in the designs and in some of the other versions, there is a little blob thing that hangs off of here, which means that if the cogs do get stuck into an odd position, because it's base 10, that little thing basically says, no, the cogs have done something weird, don't trust the answer. It doesn't tell you why the answer is wrong. There's none of this clever, bit encoding to say, oh yeah, you must have even parity here, this is where the mistake is. Just, there is a mistake. And in the docs, what it essentially says is the thing which pops up there is called a flag. Right. Good question. Any other questions? If you do have a hand up, you may also shout because the lights are blinding. No? This means I really can go down the pub now, right? Yes, excellent, thank you.